In this video, we have an example of power spectral density whereby we take a digital signal, that is a digital binary signal in terms of ones and zeros, which is random in nature. And since it is random, so we cannot take the Fourier transform directly, but instead we'll move towards an autocorrelation function and then take the Fourier transform to find the power spectral density. So we have expressed the mathematical expression of time autocorrelation function in the earlier video, that is g of tau. Tau is the time delay. Limit t tends to infinity 1 by t and integration of minus t by 2 to t by 2 g of t minus tau. That is, we have this signal which is g of t, and g of t is a signal which is random, and we take the delayed version of this signal over here, and then we find the similarity by means of this integration, and then we average it out to find the autocorrelation function. So from this time autocorrelation function we can then find the power spectral density. So now let us move towards the example. So we say that we are having a random digital signal and it contains 0 and 1, and we denote 0 by minus 1 volt and we denote 1 by plus 1 volt. So this is the first information. So the second information is that each bit, that is 1 or 0, so this has a time duration of time period of a bit, that is TB. Moreover, the actual time in which the bit is basically plus 1 or a minus 1 is half. That is, we have a return to 0 or z after time period of a bit by 2. So that is after half the duration of time bit, whether we had a 1, so it would return back to 0, and if we had a minus 1 it would return back to 0. So this is the duration of a bit, total bit, and this is the active period. So say this was plus 1 and this is 0, this is simply TB by 2. This is what is meant by condition 2. And finally we are saying that probability of 0 is equal to probability of 1, and this is 0.5. That is, bit 1 and 0 is equally probable. So we have these three informations of a random digital signal. Now let us take this random signal, any random signal which is 1, say 1, 0, 1, 0, and based on the preamble above, this is the duration of bits, that is, this is the time period, that is TB, and for plus 1 we have a voltage of plus 1 and it is terminating at TB by 2, that is, it is returning to 0, and after that again for 0 we have a minus 1 and then it returns to 0 and so on. Now since this is a random signal, so since we cannot take the Fourier transform, we have to move towards autocorrelation of this signal. So the time autocorrelation function is simply a limit t tends to infinity 1 by t minus t by 2 to t by 2 g of t minus tau d tau. Now as the first step, I need to get rid of this t, and the reason for that is because I have now bits rather than the complete time. So the first bit takes the time period of TB. So t is the total time t which tends to infinity, and this is equal to time required to send one bit, that is TB, times the total number of bits. So let us say we have n bits. So we can change t equal to ntb. TB is the time period of one bit and we have n number of bits. So hence this equality can now be rewritten as 1 over t changes to n TB. Similarly, we have minus n TB by 2 to plus n TB by 2 g of t minus tau d tau. And moreover, in this limit, TB is fixed and n is increasing. So hence this n now would be approaching infinity. The more the number of bits are there, that is if it is infinity, so the total time would be infinity. So in this autocorrelation function, as the next step, we need to solve this integral. In order to solve this integral, let us redraw this g of t. So this signal, the yellow signal, is basically our g of t. Now we denote the delay version of it by a green signal. G of t minus tau means the delay by tau unit. That is, we are having g of t minus tau, and based on the value of tau, we are moving it towards the right or left. For the time being, let us consider only the condition of delay, that is movement towards right. So we say that this tau is actually between 0 and TB by 2. This is the first condition, and the second condition is that this tau is between TB by 2 to TB. So that is, we have now an autocorrelation function in tau. We are starting from 0 and then we are assigning a value which is TB by 2 and then TB and then so on. So as mentioned, now I'm just considering the delay for the time being, and later on we would look into the time advance as well. Now consider that this is the delayed signal g of t minus tau. Now if the delay is 0, so this signal will be superimposed on g of t. But as we move towards tb by 2, that is towards the right side, we would have this region which is an overlap region, and the overlap would be until this point. After that, the overlap is 0 because this signal is not overlapping with this signal, so hence this area would be 0, right? So this is the reason that we are mentioning that we are having a delay in two cases. That is, the first one is between 0 to TB by 2. So this is TB by 2 until here, because after that this integration would be 0. So let us fix a point, say this is the point of delay within this range. So that is, we are having a g of t which is the yellow signal, and then g of t which is the green signal, which is g of t minus tau. So the overlap region in this spot is simply this one. Note that from here to here again we have TB. So the duration until here, this is TB by 2. So in order to find this part, we have to first find this part, and and this part is simply the amount of delay, that is tau. So therefore this region which is mentioned over here, so this is simply TB by 2 minus tau. That is, we are extracting this part out from this signal. So this was tau and this is TB by tau. TB by 2 minus tau, and this is the part that is needed in the integration, that is this integration. So in the first case, when we set delay which is less than TB by 2, now this turns out to be simply TB by 2 minus tau, but overall we have n such bits. So this was simply for one bit over here, but we also have total number of n bits. So the overall integration we are multiplying with n. So whole of this part turns to n TB by 2 minus tau, and the remaining part is 1 over n TB with limit n tends to infinity. So this is our autocorrelation function when the case of tau which is less than TB by 2. So we can cancel n, and if we cancel n in this expression we would not have any n left, so we can remove the limit. So eventually we have simply 1 by 2 1 minus 2 tau by TB. This is our g of tau when tau is less than TB by 2. So let us plot this function. So if we set tau equal to 0, so this part would become 0 and we would simply have 1 by 2. So over here, that is or g of tau at 0, we simply have a value of 1 by 2. Now let us look at this limit which is TB by 2. So that is, if we set now this TB to TB by 2, so whole of this would simply be 0 because we would have a 1 minus a 1, so overall it would be 0. So by setting tau equal to TB by 2, we have a value which is 0, and this is linearly decreasing. Now with this we have covered this part. Looking into the second part, we have already mentioned that when the delay is over here, there is no overlap between these two. So for this, the autocorrelation function would be equal to 0. So hence we have a 0. But note that the delay is also having a third condition. That is when tau is greater than TB. So this means that the delay of this signal is having an effect on the successive bit, and similarly this would have an effect on this bit, and this would have an effect on this bit, and so on. So for this case, when t is greater than tb, what would be the correlation? That is time autocorrelation function. And for that we have to revisit the question again, wherein we have mentioned that probability of 0 is equal to probability of 1, which is equal to 0.5. So if we multiply the delay of this with this signal, so eventually we would have a minus 1. But at the same time, the delay of this with this is a plus 1. So we have a plus 1 and a minus 1. So statistically speaking, the overall average or the time autocorrelation function would be 0 if the delay is greater than TB, if it is beyond this point. So this is only valid if we are having the condition of zeros and ones which are equally probable. So hence it would return to be 0 for tau greater than TB. So now we have this function which is RG of tau. It has a peak value at 0 and it depreciates until TB by 2, and after that it is just 0. But this is simply for the time delay. What about time advance? So again we notice that this signal, that is g of t, belongs to real number or real signal. And for real signals, we have set the condition that it is an even function. So hence we can say that this or g of tau would have an even function. At minus tb by 2 it would drop back to 0, and after that it would continue to be 0. So therefore we can express this or g of tau, which is simply a 1 by 2 1 minus 2 tau. But since we have make use of the even function, that is the property for real signals, so we are including this absolute tau herein by tb, under the condition that absolute value of tau is less than tb by 2 and it is 0 otherwise. So this is our time autocorrelation function. Now if we take the Fourier transform of this signal, we would achieve the power spectral density. And for that, let us replot the original signal, that is the autocorrelation function, and we're saying it is having a value of 1 by 2 at 0, and it is from minus tb by 2 to tb by 2. This is tau. So this was our r g of. So you may observe that this is simply a triangular function, and it is simply 1 by 2 delta of tau by tb. So we know that for the triangular function, the Fourier transform is simply a sin square function, and this is simply pi f tb by 2, and the 2 would come out as well, so we would have a 1 by 4. So this is our sg of f, which is simply at 0 there will be, this is simply tb by 4. So at 0 we have tb by 4. So this would relate to 2 by tb, 4 by tb, and so on. We have minus 2 by tb and minus 4 by tb and so on. So the sin square function would be having this shape. So this is basically the plot of our power spectral density. So using this power spectral density, we can now understand that roughly 95% is in the bandwidth which is 2 TB. So as a summary, if we have random signals, we find the autocorrelation function, which is time autocorrelation function, and then we take the Fourier transform of it to find the power spectral density. And using that power spectral density, we can find the amount of power which is contained in a particular band.